What is the problem they want to solve?
Computational speed and requirements for texture processing.
Okay. So what is a texture? Or what is the texture? You think of textures like things you touch. But what is the texture in images? These kind of things. This one here. These kind of things. They have different textures. Okay, so it is kind of background, but a structure background. And actually, if you have to describe textures, what do you think it is the best tool to describe? What is different between this image and this image, or this one and this one? How can you describe that mathematically?
Maybe taking into account the edges.
The edges. Okay, so the edges are certainly different. Yeah, that is true. But there is also something. How can you encode
Normal map?
normal?
No.
Normal map. What is that?
No, but that's for 3D textures. It's when you want to give a material to I don't know, to a 3D model, you can not only select the face, for example, only the bricks close, but also if you want the player to go near, so that the normal map indicates which edges or which parts are forgive like a three-dimensional perception of plane texture.
Okay, so it is a surface, and then you define that every point
Yeah,
is a normal to that
yeah,
surface.
it's normal. So when you go nearby, it has like.
Okay, I would say, and not only me, many people, one of the best characterizations of those kind of images is through the autocorrelation function. Okay, so let's say that we have an image, right? So we have an image, and we have a certain pattern here, like let's say they are kind of bricks. Okay. So kind of bricks here. So what is different between this one and this one? Let's say, I1 and I2. So if you take a pixel, anyone, take it, and you study the nearby pixels, you take the same here, you study the nearby pixels. They have different kind of relationships. For instance, this one has most of the pixels are of one color. So let's say that these are black, while these ones are white. But here it doesn't happen. Most of them are white. Most of them are white except a few. Okay, so how can we encode that? Okay, so let's you may remember the autocorrelation function of in one dimension. So in one dimension, this was the expected value of the product between x of n and x of n minus plus n. And we were saying that this was the lag, so this was called the lag. And okay, so we can extend this idea to pixels. Okay, so let's define the autocorrelation of an image. of the autocorrelation of an image. Now we will have a lag that is a vector. We have 2 dimensions. But it will be the same. It will be the expected value of an image at the given location times the image at that location plus the lag. So what it means is you consider different lags. Let me enlarge this. So this piece is this one. So you consider this is your point R. This one here is the point R plus M. So this is the lag. So you consider different lags. And for each lag, you compute what is this expected value. And this expected value somehow is involving, not somehow, it is involving this pixel and this pixel. And you do the same. You see that it depends only on the lag. So you have to do that operation for all possible locations. So you have your image, and then you place your square here, you analyze those expected values, and these ones and this one. So you place them everywhere. And once you have placed them everywhere, for every one, you will have, these are the central points, and these are the points given by the lag. So this sum here, this expected value, is taken over all these points. So the interpretation of that is, okay, given a location R, what do you know? What do you know about R plus M? That is the meaning of the correlation. This is the expected value of R plus M, given that you know R. But actually, this is a moment. Do you remember moments in statistics? So you had the first moment, second moment, third moment. It's a moment. So it is a moment of what? What is the absolutely ground truth? Something that contains absolutely everything. This is the joint probability distribution. So the probability distribution of I of R and I of R plus M. So this is a joint probability distribution. Okay, so you will have 2 axes now. So we are used to probability distributions with So you are used to think of these probability distributions that are one-dimensional. For instance, this one here, and it tells you, okay, what is the likelihood that x takes all these values, and then it is given by the curve. Now you will have 2 axes. So you will have an axis that is IR. What is the pixel value at the location R? And what is the pixel value at the location R plus M? And then you will have a surface. So let us draw surfaces here. So this is blue. And here, let's say it is also kind of Gaussian. But now it is 2-dimensional. So this would be P of I R plus M. Okay, so this surface here. So what is the likelihood that I of R takes this value and I of R plus M takes that value? Okay, so autocorrelation is a kind of, is a moment of that distribution. So correlation functions are something that have been very much used for this, but the absolute all the information is contained here. And if you think a bit about these things, you see that the joint probability distribution of this image is different from the joint probability distribution of that image. Okay, good. So that is the problem they want to solve. So classifying, so you are given an image, you are given a database of textures, and I present you a new one, and I ask you, okay, which of the textures you are looking at? You have to answer that question automatically, so the computer needs to know. And what do you think that could be useful for? In biomedical imaging, what would be a good application of that?
For example, for distinguishing between tissues.
Yeah, that's it. That's it. That could be a very good application. So, for instance, here, you can have histological sections. So you have this kind of, for instance, this one. This one is. You see, you have different parts in different regions of the image, and each different layers, they have a different texture. What differences one from the other are textures. Also colors. For instance, this one is darker than this one, and so on. But there is a big difference. That is the texture. Okay, so textures are as useful. Okay, so. How? So yeah, and you mentioned something that is very important. Why do you want to have a new method? So there are only, I would say, mostly two reasons to have a new method to solve a problem. Which ones do you think? So at the moment you have existing methods to solve this problem. Why would you come with a new method? Memory is, so performance in general. So either it is cheaper in memory or faster or can be solved more efficiently, or what is the other?
You need it for doing more things than it actually does.
Say it again.
So you have encountered a problem where the actual method does not work. So
Yeah.
you need to develop now.
Yeah. So the current method works normally, but in particular cases it doesn't work. And then there is a third reason. Your new method works better in general. So in more situations you work better and produce better results than the other one. So the motivation for this one was performance. Okay, so yeah, let us start defining a few things. And that's some small details that I will skip. So equation 2 and equation 1, those are the ones. Can I draw here? Is there a tool to draw?
On the sides of the border.
Yeah.
No, it's up in the upper part. I think.
Again?
I don't. Maybe in.
Edición.
Maybe on the left side of the word, I don't know if you can see the
Yeah.
I know. Up near the paper bin, I think it's no the other one. I think it's no.
Okay, that's it. So this one here, you see the structure of the you see the structure of the lag. You see this is R, KL is the R, so it is the location that you are looking at, and D1, D2 is the lag. And then you are counting this C, so this is cardinal. Cardinal is a count. How many times something happened. So it is how many times a given pixel is I, and then the lab pixel is J. What is that? That is this probability distribution. This joint probability distribution. This is this one. You see, this is equation 2. This is equation 2 in the paper. So it is how many times, what is the probability, or related to. Okay? These are probabilities, the other ones are counts, but you know the relationship between histograms and probability density functions. But what is the probability that this takes, so this equation 2 was written as Cij. So this I count that this one takes value I, and this one takes value J. Okay, so this axis will be I and J. Okay, good. Then, and if you divide by the total number of pixels, then you have an approximation to the underlying joint probability. Okay, so now you have a two-dimensional vector. Okay, so this is in the name of the. Let us call this one. In the paper, he calls it I1, Y1, and Y2. Okay. So you have a vector Y that is Y1, Y2. That is a vector formed by a given pixel and the pixel at the line. Okay, so this is a two-dimensional vector. So if it is a two-dimensional vector, it must have a covariance matrix. So it must have a covariance of Y. So a reminder, what is the covariance of a vector, multidimensional vector? So it was the expected value of Y minus the mean of Y. This was a vector. And then Y minus the mean of Y. This is also a vector transpose. And let us analyze the sizes of this. So this is 2 times 1. This is 1 times 2. So the whole thing is a 2 times 2 matrix. Okay, so this was the second order moment of that vector. And mu we didn't define. So these are vectors. So this is the expected value simply of Y. This is very easy. Okay, good. So this is these are the equivalents in one dimension. This is the equivalent of the variance, and this is the equivalent of the mean. And you know why do you want to characterize the mean and the variance? So the mean gives you where this is going. So whether this is shifted to the left or right or whatever. And the variance characterizes how wide this is. Okay. So this is the same. So we are characterizing what is the centroid of this probability density function, the mean, and how wide that is. Okay, good. Then a vector, it has a covariance matrix. And if it has a covariance matrix, so you see the same kind of definitions that we have. That is an interesting property. Okay, so in general, this mean will have 2 different components. So in general, you will have this mean will be mu1, mu2. In the sense that the first component will have a mean, the second component may have a different mean. But we are taking vectors from, so those two vectors are these 2 points. So what are the image values at these 2 points? So there was a comment at the beginning that it said that we were assuming that this image here, so the whole image, is stationary and ergodic. Okay, so what do these words mean? So have you found these 2 words before in stochastic processes? Yeah. So what is stationary? You know, probably for time, but the idea in the space is the same. So stationary means the statistical properties do not change with time or do not change with space. Okay, so what are the statistical properties? So the mean, the covariance, the autocorrelation function, all these things, they don't change over space. So, and that is what characterizes the detection. If you look at the detection here or there, they more or less they look all the time the same. Okay? And ergodic is a little bit more complicated. Do you know what ergodic is? Have you found ergodic before? No. Okay, so ergodic means I will explain it in one day. That is easier to explain. Okay, so let's say that we have a random process. Okay, we have an example of a random process. You are measuring, I don't know, whatever that is, and you get something like that. So every point, what is a random process? A random process is a collection of random variables. So if you look at a particular time, x1 at t naught, this is a random variable. And if I observe again this random process, then I have a different observation, and then it has more or less the same kind of appearance, but the specific values are different. So if I look at the game at this time, I get something different. And every time you observe this process, they all more or less look alike, but the specific values are different. Okay, so this is the characteristic of noise space. Okay, now you wonder the following. Okay, so let us, this x2 has a mean. So if I have multiple observations of my random process, I can compute not x2, and this is x3, this is x3. If I look at the mean of all these values, so at t naught, this random process x of t has a particular mean. So what is the mean? What is the expected value of x at t naught? Has a value. So if I observe it many times, I can compute the average, and that will be an estimate of that value. Okay, but very often you don't have many observations of the same process. You only have one observation. And then you may wonder, okay, I don't have multiple observations at t naught, but I have multiple observations in this direction. Can I compute the mean of those observations? And that will be equal to the expected value at a particular point. And if this fulfills, if this is true, then it is a polygon. This is one way to see it. There are multiple ways. They are all equivalent, but they highlight different properties of Ergodic processes. Okay, but ergodicity means I can substitute multiple instances of my process by a single observation, and I can compute things in a single observation. And what I estimate, everything like the mean, the variance, the correlation, the probability, the joint probability distribution, and everything will be approximately the same, and in the limit they will be the same. As if I repeat the process multiple times and I do it through. Okay, good. Okay, so in general, these two means will be different, but I am assuming that my image is stationary and ergodic. That means that this mean here and this mean here will be the same. And the variance here and the variance here will be the same. You see? So my image will have particular structure. So it will have a single mean, mu1 and mu1. And my correlation matrix, that in general, it is like this. So it is sigma 1 squared, and then the correlation between the two, sigma 1, sigma 2, the correlation between the two, and sigma 1, sigma 2 squared. This is in general that matrix, that is covariance matrix. But the variances are the same. So sigma 1 and sigma 2 are the same. So I can take it out. So if I can take it out, whatever remains is sigma squared, and then 1 rho 1. And this is true. Let us write this. So this is true because of the stationarity. And this is also true because of the stationarity. If they are not stationary, this step is not true. This step is not true. But if it is true, it has this structure. And that is what we have in the paper. You see? This one, and mu, there is a single mu for both. Okay, then. Do you remember eigen decomposition? So the eigen decomposition of a matrix. So we will look for a couple of, he's calling this one CY. Okay, so there will be vectors that, in general, if I take a vector, multiply by a matrix, I take a vector U, and multiply by a matrix, I will get a vector P that doesn't have anything to do with U in general. But there are a few vectors such that when I multiply this one by U, I get lambda times U. So there are a few vectors that when you have this is two-dimensional, so I'm fine here. So I have U1, U2. I have this vector U, and when I multiply this vector U by a matrix, what I get is the same vector in the same direction, but now multiplied by lambda. And lambda can be larger than 1 or smaller than 1. Okay, in general that doesn't happen. There are only two directions that in which this property happens, and these directions they are called the eigenvectors. So this one are the eigenvectors. And these ones here, they're with the eigenvalues. And they're nice because they define the basis. So this vector, let's say this one here is an eigenvector, and this one here is also an eigenvector. They are orthogonal to each other. And these two will define the basis in which many nice properties occur. Okay, so let's look for the eigenvectors. So this is this equation. So let's look for the eigenvectors of our correlation matrix. And because the correlation matrix has a particular structure, you can compute what are the eigenvectors of the eigenvalues of that matrix, and these are the eigenvectors. Sorry. These are the eigenvectors, and these are the eigenvalues. And this square root of 2 is simply to make them unitary, so that make them unit vectors, so that the length of the vector is 1. But if you don't care about the length, then the two eigenvectors are this one, 1, and 1 minus 1, 1 minus 1. And there are eigenvectors that are multiplying what? They are multiplying this kind of vectors here. So we now see when I multiply u1 times I, y, what I have is I of r, and then times this one, this is transpose, plus I r plus n. And the other one, u2 transpose times y is equal to IR minus IR plus n. So that means that differences and sums are important things to look at. Okay, so let's go on. So we will now construct this set 1 and set 2. Set 1 and set 2 are the ones, except for the square root of 2. But the square root of 2 you don't care, because that is a scaling factor. So this is set 1, this is set 1, and this is set 2. And there is an important property. Now I can construct a new vector set. This set 1, set 2. But the covariance matrix of set will be some sigma, 0, 0. So they are uncorrelated. Uncorrelated doesn't mean we have two properties that are somehow similar or related. The other one is independent. So independence implies uncorrelation, but uncorrelation does not imply independence. Okay, but these two are uncorrelated in general. Okay, good. Then, they are uncorrelated, and the variance is this one. Okay, and the covariance between the two are 0. Okay, now, you know, I'm sure you know about this. So let's say that we had an original vector I. We have transformed it into a vector set. Have we lost information? You may remember, you lose information if you cannot recover, given set, you cannot recover y. But this transformation is invertible. So if I give you set 1 and set 2, you can solve for I, and then you recover the vector y. So it is invertible. So if you have a probability, the joint probability distribution of y1, y2, you can compute this as a function of the joint probability distribution of z1, z2. This is a function of this. And you may remember this when you were doing change of variables in multivariate statistics and computing joint probability distributions. Did you? In statistics, you did these kind of things, right? You don't remember probably. You don't remember, but given the probability distribution of 1 and a change of variables, you could compute the probability distribution of the other. Okay. But now, set 1 and set 2, they are uncorrelated. They are uncorrelated. So they are actually this function in general. So in general that is true, but in this particular case, if you make the change of variables, they are the same. And this, and again, this is true if that set 1 and set 2 are independent. This would be the probability distribution of 1, and let us call this. So this stands for sum. Set 1 was the sum, and D was the difference. So this is true. This step is true if it is independent. What if we know they are uncorrelated and they may not be independent? Okay, so let's say this is approximately equal in the case of uncorrelation. Yeah, so I have a way to compute, approximate this joint probability distribution based on the probability distribution of the sums and the probability distribution of the differences. And here is the saving of space. So look at this. This is a two-dimensional probability distribution, but it can be decomposed as the product of two one-dimensional probability distribution. So let's look at this. So think of the sizes for an image. Okay, so let's say that we have an image. So we have here whatever image it is, and whatever texture we have in there. And the values here, I go from 0 to 255. And we want to construct this probability density function. So you have to count how many times this pixel, and this one, separated by a given lag, take particular values. Okay, so I here, and j here. You have to count and you have to analyze this segment in many locations, in all locations in principle. And you have to count. Okay, so how large is this matrix? So I have to count how many times I takes value 0, value 1, value 255, and j takes value 0, 1, 255. How wide is this matrix? Two to the 8, it is 2 to the 8, and the product is 2 to the 16. So I have to store 2 to the 16 values. And that for every lat. For every lat, I have 2 to the 16 values. Okay, what about the other one? What about this one? So, if I and j take values between 0 and 255, set 1 takes values between 0 and 510. That is the maximum value we can have. And what about the difference? The difference takes values from minus 255 to 255. No? That is the maximum range of the differences. How many bits do you need for that? 9, and here to the 9. So you need 9 bits. So instead of storing many matrices of 2 to the 16, I have only for everyone, I have to store 2 to the 9 values. So that is 2 to the 10. So this solution is 2 to the 6 times more efficient. This is 64 times more efficient. It is relying on one property, that is that you can do this approximation. If you cannot do that approximation, you are done. You are dead. Okay, but if you can approximate, okay, then I need 64 times less memory. And what else? So let me see what they have. Yeah. So next equations. So far so good. Yeah. Okay. So yeah, there are a few details like this one. If you want it to be a probability, you need that the sum of all these values is 1. So you compute C0 such that this is 1. And then all these equations here, I will skip them today. And what they are trying to measure is, okay, we are assuming that these two things are equal. Okay, that this one is equal to this one. Are they really equal? So can I compute the kind of distance? What is the distance between this probability density function, the joint, and the approximation, given assuming that they are independent. So what is the distance between the two? If they are equal, this distance should be 0. And then what he's measuring is not the distance, but the idea is to measure something that if both are equal, then you get 0. That is the information, so the level of the relative entropy. So this is called the relative entropy between P and P. Have you seen entropy before? Yes. So this is the relative entropy, and okay, so we will not get into this. But the idea is, okay, we have assumed that these two are equal. So the key of this article is this equation here. So this one here. That is, we have decomposed something that is two-dimensional into a product of two one-dimensional things. And then, okay, so we haven't classified textures yet. How do we do that? Okay, so we will now look at the article again. So yeah, we will need the histograms or the probability density functions of these sums and differences. And at some point, you will have to classify. Okay, so you will take a texture image, and so it has two phases. And this is important to understand. So this process has two phases. So the first phase is learning. So in this phase, you are given a set of textures, and another one that is this texture here, and a set of textures. And then from every one, you have to look at the probability density functions of the sums and the probability density functions of the differences for different lags. So for every lag that you consider, you will have different probability density functions of sums and differences. And the same for this one. So for every one, you have different probability density functions. So you have to learn this. Okay, the second one is, in general, this is called inference. This problem is called inference. That is, you are given a query image. This is a query image. And you are asked, okay, from all these textures, which one is it? And then what you would do is, okay, you would compute here the sum and differences for different lags. And you will compare these ones to this one, and this one to this one, and this one to all of them, and decide which one is most similar. So this part of the paper is describing that you have to estimate the probability density functions of the sums and the differences. But then, for making the comparison, you have a full distribution there, and it is a bit inconvenient to compare distributions. So, what if instead of comparing distributions, we compare numbers? So why don't summarize? Let's say that you have a particular distribution here. So one of these. Let's say that one of these guys here. So one of these guys here for a particular lag, it looks like this. Right? It looks like this. If it is a sum, it cannot be negative. So it looks like this. Okay? And this is the sum. This is the PS at that particular lag. Okay, so why don't I summarize that distribution into a few numbers? What are the few numbers that are reasonable? I can compute the mean, I can compute the variance, I can compute what else? I can compute all kind of moments, but huge moment about the mean. Okay, so and you have there the formula. So the formula is the standard one. And you can summarize through the entropy. So you can compute the entropy of that distribution. I didn't want to get into entropies, but just I think at least this idea, I think it is interesting that you know. So you may have a distribution that is uniform. And so this is the probability of S, and this is epsilon. And you may get the distribution that all the time you get the same value. And you compute the entropy of this one and the entropy of this one. So let's say this is H1, and this is H2. Which one is larger than the other? This is the largest entropy you can have. For the uniform. So this one is much larger than this one. Actually, this one is 0. So if you don't have any variation, you always get the same value. The entropy of that distribution is 0. And this is the maximum entropy that you can have. The uniform distribution is the maximum entropy. And the formula is this, actually, this is very nice. You know Shannon entropy, right? So this is called Shannon. It is the expected value of the logarithm of pi p with respect to the distribution p. So that is minus the sum over all p values. This over all s values of ps logarithm of ps. So that's sum. And what are the units of that? How do you measure entropy? What are the units of entropy? Beats. Okay, good. Then you can measure entropy. So you can summarize the whole distribution to a few numbers. And here you have more numbers. So these numbers are, okay, I may look at this summary for the joint distribution. So I can define what is the mean of the joint distribution, what is the variance. I can compute all these summaries. Can I compute the equivalent with the sum, the probability distributions of the sums and the differences? And you can. So whatever summary you compute here with the joint, you can compute here using only the differences and the sums. Okay, so that is what is explained here. So given a histogram, you can summarize with global features. So global features are global numbers that describe somehow that histogram. But we haven't classified yet. Okay, so let's classify. Okay, so the first classification will be done with the raw histogram, so not with the summaries. And the second one will be done with the summaries. So the first classification is, okay, so I have drawn here kind of continuous distribution, but this is not continuous because the sum of two image values, either it is 0, it is 1, or 2, or 510, but it cannot be 2.5. So this will have samples. So we will have samples of this. So I can put all these values. In a vector. So I can define a vector that will be, what is the sum? Let us use histograms. So what is the histogram of 0? What is the histogram of 1? What is the histogram of 510? And this is my vector. Okay. So I reduce histograms to vectors. Here I have a vector. This transpose is simply to make it a column vector. Now, I can ask, okay, what is the probability if you divide this by n, if you divide the histogram by n, you have an estimate of what is the probability density function. So what is the probability of observing? So remember, we have learned PS, PD for the textures. Now I have a query. In this query, so I will have a, for any given sum or difference, I will have a vector. So now I may wonder, okay, what is the likelihood of observing x? So this x is coming from the query. It's coming from the query. Given that the true texture is this one, is I don't know, image 1. These are image 1, image 2, and so on. So given that it is coming from I1, and I will compute the same for all the others. Okay. So I will compute what is the likelihood of coming, given that this is I2. And I have to ask that question for every lag and for every sum and difference. Okay. How do I compute these probabilities? How do I compute those probabilities? These histograms look like this. Okay, so that means that these are fractions. Okay, the sum of all these values is 1. So let's say, just to put this in numbers. Let's say that this value here is 1 over 100. This number here is 1 over 155, 105, and so on. So, what is the probability? This is a multinomial distribution, isn't it? This is multinomial. Do you remember the binomial? The binomial was the how many times? So if the probability of getting a head in a coin is 0.5, what is the probability of getting 5 heads in 10 rows, in 10 throws? Okay, that is the binomial. So if the probability of getting all these sum values are these ones, so this is the equivalent of the coin, what is the probability that if I have a query image, I see this many zeros, this many ones, this many twos, this many whatever, 510. So this is the equivalent problem of throwing coins, but now we are not throwing coins, we are throwing pixels. And each pixel value has this probability. So, and the multinomial distribution was this one. Okay, so this likelihood is computed in this way. So we here know everything. So X is coming from the query, Pj is coming from the length. From the length section. And you would have, so yeah. So which one would you take? The one that gives maximum 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 likelihood. But actually, maximizing this likelihood is equivalent to minimizing this. We are making a big jump here, but we are not making this proof. But maximizing this likelihood is the same as minimizing this distance. So now, again, we see that xi are the histograms of the sums of the histograms of the sums or the differences. And these p's are coming from the textures that you have left. So you are comparing your query image to the textures, to the distributions that you are expecting from the length textures. And you would take the one that gives you minimum distance. So you can think of this as a distance. So you would take the one with minimum distance. And the next one, instead of going through the histograms, I can go through the image. And now I'm using the raw image values. I'm not going through the histograms anymore. So even you don't need to compute even need to compute these histograms and store them. You don't need to compute these ones. So you only need to compute these ones for the textures down here. For the textures you need to compute, but for the query image you don't, because you can loop over the input image, the query image. Okay, so that is one way to classify. What is another way? Okay, so instead of, let's do it now. I don't know. Explorer, I'm running out, of course. Okay, so instead of making these summaries with these distributions, we will construct summaries. And I will have the summary of texture 1, the summaries of texture 2. And we know what kind of summaries we're computing. We are computing means, variances, moments, entropies, whatever you want. But from a histogram, you compute a few numbers. And then yeah, so these textures are not allowed. So you don't have a single example of these textures. You will have multiple examples. You will have another one here that it looks more or less the same, but the image is different. You will have another one and the same here. So you have multiple examples. For every example, you have one of these summaries. Okay, so this one is the summary of the first texture, but it is the first instance. Then you have the summary for the first texture, but this is the second instance, and the third one. And now you consider all these vectors. And you say, okay, I will assume that these vectors follow a multivariate Gaussian, multivariate normal. And if it is a multivariate normal, so dx coming from a given texture is coming from a multivariate normal with a given mean that I don't know, I will have to compute. But it is the mean of the summaries of the texture 1 and some covariance matrix that, to avoid confusion, we will call it R. Okay. And this is a matrix, this is the covariance matrix. And then I can compute, okay, for this new image, for the query image, I can also compute the summary. I can compute the summary of all these all these histograms. And now, for the classification, I compute the same. So what is the probability, what is the likelihood that I observe, that I observe this summary given that it is following from texture 1. This U1, R1, and the same for all the others. And then you compute these probabilities, these likelihoods. How do you compute the likelihood? Okay. Here you have the expression. So it is something that depends on the query. The query is X, and depends on the texture you are looking at. It is the mean, MJ, and the covariance matrix, RJ. So this is even cheaper, because now, for all this, I don't have to keep all these histograms. All I need to keep is the mean and the covariance matrix, that are much known. So that is the method. Let's see if the method works. Okay, so we have a number of textures, and he's considering a few lags. So the lags so you take a distance, and then that distance at 0 degrees, at 45, 95, and whatever. Okay, then we have here the whether there are good approximations or not. This we were saying all our method is based on the assumption that uncorrelated values, the set 1 and set 2, they are uncorrelated, that's for sure, but they are also independent. Is that true? And we have for that this relative entropy. Okay, we would like it to be 0, but they are sufficiently small numbers. Okay, so they are sufficiently independent. And then we have here the results with the classifications. So this is classifying those textures using the sum and difference histogram, using these directions, and this is probability of correct classification for the training set. And this, I think it appeared the other day. So typically when you have a data set, you split it into parts. One for training, another one for testing. Okay, so in the training set, so we said we have multiple examples. So let's say that you have 10 examples of this kind of texture. So you will take 7 for learning, and 3 for checking that you got correctly classified them. And these 3 you never learn them, so you are blindly trying to classify them. So what is the probability of classifying them correctly? And it depends on the patch size. So what is you divide this into small pieces, and depending on how large the piece is, you may go from 91% of correct classification to 100% of correct classification. And this is using the sum and the difference histograms, using only the sum, using only the difference, and using the covariance matrices. Using the covariance matrices, they are better. For instance, for small patches, they classify 96%, while the other ones, the sum of histograms is only 59, or this one is only 89. So there is more information in the covariance, in the joint probability distribution. But but this is much more costly. I need to compute more and I need to have more space, while this one is sufficiently good and it is much cheaper. And this is the same, but now using the global measures. So these summaries, this purple summary, are normals. This one here. And they're a little bit worse. You see, 88, 91. But if the patch size is large, then you have 100% of correct classification. So we have simplified a lot the problem. So I'm sure that you have learned now more than on your own reading. But what is important is that when you take an article, you understand what is the problem they are solving, how they are solving it, what are the meaning of those equations. So equations is simply a way of expressing ideas. But you have to take the idea. What do they mean by this? And why this is important? And that is what you have to explain in the exam. An application. So this is the kind of stuff we do at the CME. So we try to look at the structure of macromolecules. Macromolecules can be just a small protein, or it can be a whole virus, like in this case. So this is the virus we constructed from one way, and this is the virus we constructed in another. And do you see that the textures are different? Which one do you see better? In which one do you see more details? Left or right? Right, you see more details. Everyone else? Two. Yeah? So you prefer right. I prefer left actually. Look at these small details here. So they are better seen here, they are much more black. You see? These ones are bigger. If you look at the small details, you see many more details in here. You see, but in here, they are more black. Right? They are like low pass filters. Okay, so can we use this? I see more details or not? You already know. It is resolution. It is what is the maximum frequency in my Fourier spectrum that has still information. And can we use this texture detection to say, okay, that one is 4 angstrom resolution, this one is 6 angstrom resolution. An angstrom, the size of an atom is an angstrom. So you are seeing here groups of 4, 5 atoms. Here you are seeing groups of 6, 7, 8 atoms. You cannot distinguish between them. So this could be one of your practices. So if anyone has not chosen yet, or you want to change, you may implement this method to detect what is the resolution of these maps. And if you are curious to know what is how do a virus look in the microscope? Sorry. So they look like this. And these are big objects. Viruses are relatively big. If you look at proteins, so you can, this virus is made of proteins. So you can look at the proteins independently, but you barely see anything. So it is a lot of noise and then small spots there. Okay. Any other question? No. Okay, so in the exam you will have to do this. So I will give you paper at the point of the exam, not before. And you will have to read it, and you will have to make a summary. And very important, it is not just talking. You have to understand the equations and explain what the equations mean. Okay? And I understand that exam is graded between 5 and 10, so no one fails unless you leave it empty. If you leave it empty, there's no help. But unless you don't leave it empty, you try to do your work. It is graded between 5 and 10. So I understand that you don't understand everything.
The exam is going to take place during the class hours.
Yeah.
Okay. Both of them?
Both. Okay, so if there are no questions, then we move on to the lectures. Okay, so we were here with resizing images. So we have an image and we wanted to make it bigger or smaller. And we saw yesterday a technique that is called pixel replication or nearest neighbor interpolation. And today we will see this bilinear interpolation. Okay, so what is it? So bilinear interpolation, so let us remind what is linear interpolation. So linear interpolation is you have a signal, x of t, and then you have samples, this signal, and all you know are the samples. You don't know the underlying signal. And then you are asked, okay, what is the value of x t prime? Then a possibility is you join these two with a line, you evaluate that line at that point, and okay, it's not perfect. We have an error, a small error, but it will be an approximation of what the value is there. But it is certainly better, that approximation, than any one of these two estimates. So we could give this estimate or this estimate, but this one will be better than any one of those two. So those two, let me use a different color, those two are called nearest neighbor. Nearest neighbor interpolation. This one here is called linear interpolation. Linear interpolation. This is nearest neighbor interpolation. Okay, so let's do that, but now with images. Okay, so this is a reminder of what was nearest neighbor interpolation. So we had the values at these points, the red points, and we copied that value to all the squares. So we were doing their magnification by a factor 4. So we will copy that value to the 4 times 4 block. And we want to have this. So somehow you see that along this block is going from gray to dark, but it goes in steps. So can we do something that goes more gradually from gray to dark? That is what we want to achieve. And we have been talking in this direction, but the same in this direction and in this direction. So we want to have a smooth transition between this value and this one. For instance, let's say that we have this problem again. And we have this sample, and I will exaggerate them. Sorry, these are green. have this sample, this one, and we want to produce two intermediate samples. So we want to produce this one and this one. So you already know the solution. You already know the solution. So what is the best estimate of this one? How do you, this is x, this is x of n, this is x of n plus 1, and this is x of n plus 1/3. Okay, so what is the best estimate of x of n 1/3? How would you compute that? What about this? 2/3 of x of n plus 1/3 of x of n plus 1. Is that fine? So what about this one? X of n plus 2/3 would be 1/3 of x of n plus 2/3 of x n plus 1. You're fitting a line actually. All of these follow this rule. So x of n plus delta are, let's see, 1 minus delta x of n plus delta x of n plus 1. You see? Even they work also very nicely. They work also very nicely for the corners. So let's calculate following this formula, x of n. So x of n, let me make it black. This is one of the ones we know. So this is x of n plus 0. So it will be 1 minus 0 x of n plus 0 x n plus 1. You don't have to interpolate, you have it. So it's simply copy. And the same here. So if I want to compute, x of n plus 1, this is x of n plus 1. So delta is 1. And this will be 1 minus 1 x of n plus 1 x of n plus 1. Okay, you have it. You have to go to interpolate. So this is linear interpolation. This is linear interpolation. Okay, so we'll do the same, but now in 2 dimensions. Okay. Okay, good. So how to do that? Okay, so let's say that we have these 4 values that we know. These are the equivalents of these 2 points. These 2 points we know. I want to fill those values. Instead of fitting a line, I will fit a plane, because we are in 2 dimensions. So I will fit a plane. Actually, if you think of a plane fitted here, you have 2 lines. So one line going to there, and one line going to there. So actually the basis of the plane are the 2 lines, and that is why it is called bilinear, because you have 2 lines, one in 1 dimension and the other one in the other dimension. So we fit the plane. There is only one plane going through the 4 points. And now I evaluate wherever I want. So I want that value in the middle, so I evaluate the plane at that point. So here we have the plane and we have the two lines. So this is one line, this is the other line. And then you evaluate the plane at that point, and that's it. You fill all of them. And we will come back to the equations later, but let us see first the effects. Okay, so we will enlarge this image by a factor 4. So let's have a zoom. So this is how the original data looks like. And now we want to have an image that is 4 times bigger in both dimensions. So we take the values that we know. So these are the equivalent, these 2 points that we know. And we want to fill the values in between. Okay, so this would be, if we simply use nearest neighbor interpolation, so we have these steps. And this would be the result if we use a bilinear interpolation. So you can see the difference between this one, that is nearest neighbor, and this one. So we go in the smooth transitions from one to the other. Okay, good. Then, the final result that using nearest neighbor interpolation or bilinear interpolation. So this one is much smoother. It might make sense. Again, more comparison. But we are not restricted to integer factors. Again, we can use non-integer factors. So I want to reduce the image by a factor of 3/7. Okay, so we know the solution of nearest neighbor interpolation. So nearest neighbor interpolation will copy these values here. But we have this problem of an uneven distribution of pixels. So here the separation is 1, but here the separation is 2. So that is unpleasant. So what we can do now is to interpolate at the value, at the red point. So I have a continuous signal underneath. I don't know the continuous signal. I only know the samples from that signal. But from that samples, I want to interpolate what is this red pixel there. That it is not in the middle of any of the points I know, but I can interpolate from the pixels around. So I think there is a nice representation here. Yeah. So this is a zoom of that area. And then I want this one I will have. So when I want to copy this value, I have that value, no problem. But for instance, this value here is in the middle of 4 pixels. But we already know the trick. So you fit a plane and you evaluate in the middle where you want to evaluate. Okay, so let's do that. So there is no problem to copy that one. There is a copy to copy that. But I can do the trick. So I can fit a plane to these 4 values and evaluate in this blue point. The same there. And the result. This is the... Okay, so now let's go for equations. Let's say I have 4 values at these points, at these locations: RC, RC plus 1, R plus 1C, and R plus 1C plus 1. So those are the points where I have to fit the plane. Then, what is the plane? So I want to evaluate at that point. What is the value of that location? So I will use the 4 values I know and with these weights. Okay, so let's see. So I will have a delta now in 2 dimensions. So I will have a delta in columns, a delta in rows. And then these are the weights I will use. And these weights, let's look at them. Let's say that our point is RC. Okay, so we are here. I want to interpolate there. What is delta R, delta C? Delta R, delta C are 0 both. So I will have 1 minus 0, 1 minus 0. So this product is 1. But delta R is 0, delta C is 0, and both are 0. So all these terms disappear. So at this location, I'm copying I of RC. That is what I wanted. What about this one? So that one, delta R will be 1, delta C will be 1. So this is 0, this is 0 because delta C is 1, this is 0 because delta R is 1, and these both are 1. So I'm copying from R plus 1, C plus 1, that is what I want, you see? So this scheme, this weighting scheme, is giving more weight to the samples that you have closer. And that is what we were doing before. So when you look at this, I wanted to interpolate at this location, so I was giving more weight to the sample I had closer, and then less weight to the other sample. So actually, if you evaluate for the 4 points, then you will see that you are taking the values from the right points, and that is the proof that this is a plane. This is a plane that goes through all those points. Okay. And how do you know it is a plane? If you, what should be the equation of a plane? So we should have it. Why this is a line? This is a line in what? What is the variable here? Which is a noun, which is the one you play with.
X of n.
No. Which is your argument? What do you vary? You go from here to there.
N.
Delta. You're changing delta. So you're changing delta. What is the degree? So if you are changing delta, this is a constant, this is a constant. Okay? Whatever the values are, but those are constants. So what is the let us do it for in 1 minute. So let us multiply this. So I will have x of n, and now plus x of n plus 1 minus x of n multiplied by delta. So what is the shape of that equation? That is a constant. It's a constant. So let's say A0 plus A1 delta. That is a line in delta. Okay, so if this other equation is a plane, what is the equation of a plane? The value that I'm interpolating, so the value that I'm interpolating only depends on delta R, delta C. Those are my free variables. What is the equation of a plane? Should be I think that's all. Yeah. That's all. If you multiply all these, you would see you have the delta R products. So you have delta R's, you have delta C's alone. So you have, for instance, where do you have delta C alone? When you multiply this times this times this, you have delta C alone. But also you would expect to have delta R's, delta C's. But if you make all the multiplications at the end, all the cross products will disappear. Okay? So all the terms in delta R, delta C, they will disappear. They will cancel each other. So you will have the equation of a plane. That is the equation of a plane. Okay. Then So now, what is the procedure to interpolate? So it is almost the same as the one we had before. So what did we have before? Yesterday we had the following. Okay, so we have an image I want to have a smaller image J, and then I will have coordinates. Let me see the names that he's using. He's using R prime C prime. So he's using R prime C prime here, and R and C here. And there is a scaling factor, S of R, that is number of rows here divided by R prime, and this one divided by C prime. These are capital C's. Okay, so then loop over R prime C prime. For every point, we will compute the fractional coordinates. So R fractional, R prime is R, and C fractional will be S C prime. So this point, this is R prime C prime, this is R prime C prime. But what we are doing by that is taking this point and transferring it to here. So this is R prime, as C prime. And we have called that fractional and R fractional C fractional. And that will be in the middle of the image. But now we don't have. So that will be in the middle, but I will take the 4 nearest neighbors and evaluate the image at the middle using that formula. And then I will have a smooth interpolation. So here you have the results of bilinear interpolation for different factors. For color images, you have to do the same, but in the 3 bands. So there is nothing special. You do the same procedure in the 3 bands. And I think it is a good point to stop. So, any questions? So, next day we